So hi, everybody. We're going to talk today about artificial intelligence and machine learning for search and discovery. I'm Jason Gilman. I'm a principal software engineer with Element 84. I've been working on search and discovery for a long time, ever since like 2005, when I started working with NASA as a contractor, working on that. And then recently been doing a lot of stuff with AI and ML. So we've got some great talks. See if I can get the slide advancing to work. Well, great talks after me. I'm going to talk about providing real value with geospatial AI ML. And we're going to try and get to past the hype around it, past the backlash, to get to understand, like, what are these tools and what are they good for? Then we're going to have Mikey Abela from Earth Genome, and he's going to talk about a really cool tool that they've built called Earth Index. And then Chad Melton from ORNL is going to talk about retrieval augmented generative LLM application and transportation safety. And then if you're at the plenary this morning, you heard about the Department of Commerce's RFI that they had out where they were gathering information. So Tyler Christensen from NOAA is going to talk about some of the results from that. We should have plenty of time for discussion and questions. So in between talks, we'll have some questions and at the end as well. So some quick gratuitous plugs. Tomorrow, we have one from my company on user experience for search and discovery from Brad Andrick. Then we're going to have in the evening, next generation search and discovery. I'll be talking there among other people, and I'm going to continue some of the topics that I bring up here there. And then we're going to have some demos at the poster and demo reception. I can show you some of the neat AI ML stuff that we've been building at Element 84. All right, so let's get to it. Providing real value. So a lot of people see AI as kind of magical. It's mysterious. It's hard to understand. There's so much hype around it, and then there's this backlash against it. So if we look at news headlines, we have things like artificial intelligence is changing the world. But then people are also saying, oh, it's overhyped. It's not providing that value. But then other people say, oh, it's time to believe that hype. It's going to revolutionize drug development. It's going to change how we work. And we'll be able to use tools that we can just ask questions and it'll go off and do our jobs for us. But still, it has a trust problem, right? We don't know, where is that data coming from that it was trained on? Like, was that taken ethically? And if we ask a question, are we going to get an answer back that we can believe? Or is the LLM going to hallucinate, which is a real problem that can happen, and I've seen it happen. And there's a lack of transparency, right? They seem like a black box. You ask a question and you get an answer back, 42. Where did that answer come from? What training data provided that? So there's this lack of provenance and clarity that you need for science. And then biases, right? If it's trained on our past, it's going to have all the biases and things that we're trying to move beyond. It's all going to be ingrained in it. So we have to take into account all of these. And then we're worried about the cost, right? How much does this cost? Models are really expensive to develop and train. They use a lot of energy. And we want to understand what's the carbon footprint, how much water is being used to cool these data centers. So there's a lot of concerns here. So I can't solve all of those today in this presentation or even this session. But I do want to talk about how it's going to provide real value and be useful in our world of geospatial analysis. So one thing I want you to keep in mind is that these are tools. Like databases before them back in the 70s, the rise of the internet, servers, the cloud, all of these things came with hype, but they also provided real value. And we can use Postgres and PostGIS to build solutions. We can do the same things with these, and it's just understanding how we use them. So we have to think, okay, what is the real value? Why are we here today? So everyone is here, and we're working in this industry because we want to provide answers to users. Users have questions. that they want to know about climate change and air pollution. They want to understand how to use their resources effectively, like water. They want to understand the impact of cities and development. And as natural disasters occur, we want to understand, like, where are they happening? Where will they happen? How do we allocate disaster response resources to do this? So this is where we look at the real value. And I'm going to use a metaphor here as a way to measure value. We have data on the right side and users with their problems on the left. And there's some distance, some work that has to happen in order to get to an answer. Users have to find that data. They have to get it in a format that they can use. They have to pull and extract some information out of it in order to come up with an answer and figure out how to display it. When we build tools like data catalogs and user interfaces, we're providing some value because we're making it easier for them. They don't have to do quite as much work because they can get precisely the data set that they need. They'll get just the data that they want, just the subset that they're interested in a format that they can use. And UIs and catalogs like this provide a general solution to a lot of users. They don't solve the complete problem. We can build solutions that solve a complete problem or that reduce it greatly when we build like a specific tool, like a wildfire portal. That takes care of almost everything, but it helps a small user base. And so we want to look at this area and see, where do these tools plug in? And one of the things that, one of the great promises is that people can just ask questions. That maybe they can ask a question and that we can do all of the steps and get all of the way to where they ask a question, we get an answer back. I don't think we can do that for all users, for all questions, for all data, but there is definitely some subset of questions and users and data that we can give answers to. So let's dive in a little bit and think about, what is the work to answer a user question? So if we're going to build something that can automatically take a user question and provide an answer back, we have to do a few steps. We have to understand the question. What are they asking? We have to identify the steps, right? Finding the data, getting the data, doing what the analysis is, and then actually executing those steps. Look at large language models. So that's the kind of the first step there, is to understand the question. So if a user asks a question like, where are the current cases of Lyme disease within 20 miles of Boulder, Colorado? We have to be able to pull out some of this information here that they're asking. We need to understand the context of who the user is, the terminology that they're using, like Lyme disease, the specificity. So what time range are they talking about? This is current, so they mean like whatever the latest data is. And there's a spatial area here that they're asking about. And then what's the expected outcome? Do they want to see a number, or they're asking where? They want to see a map. So large language models are really good at being able to do this. And I'll show some ways that we can do that. So part of a user question, right, that within 20 kilometers of Boulder, Colorado is a spatial area. And so I have a different one here within 10 kilometers of the coast of the Iberian Peninsula. It's like a natural language representation of a place on the ground. So Element 84 developed a technique where we can take natural language areas like this and be able to come up with, like, what is the precise polygon that represents what the user is asking for. So if you just take a large language model and you go and you ask it, hey, can you give me a GeoJSON polygon that covers the coast of the Iberian Peninsula? ChatGPT will say it can't really do that for you. It gives you an example one, but it says, like, we have to do some other work to really get that answered. If you take the polygon that it gives you back, I'm actually surprised. It's like actually like in the right area of the world. It does cover part of the coast. It's not a valid polygon. It's got a twist in it, which is why it's got this weird rendering error. But this is an example of, like, well, they can do a lot, not quite enough on their own. It requires something more. One of the tricks here is we have to be creative and understand what they can do. When a user is asking for a spatial area, when they're saying, like, within 10 kilometers of the coast of the Iberian Peninsula, it's almost like pseudocode. And so we can think of that as a directed graph. So they're asking for a buffer within 10 kilometers of a coastline, a spatial operation of a place on the earth that we can go look up. If we can get this tree, we can execute it. We can go back in reverse order, do a place lookup, So we can find the polygon that represents that area by doing a geocoding search. We can compute the coastline of that, and then we can add the buffer to it. So really what we need to do is get the LLM to help us get to this point. LLMs are really good at understanding language, and they're also good at understanding programming languages, or data representation languages like JSON and YAML and XML. And they've been trained on this so that they can understand JSON schema, understand a user request, and be able to map it as best it can with you give it some rules into a data structure. And all of the examples that I'm talking about today aren't custom generated large language models. We didn't train them. We're taking off-the-shelf ones like those that run in, Amazon Bedrock or ChatGPT. And with prompting techniques, we can get it to produce this. So this is the way natural language geocoding works. We take a user query, we prompt the LLM saying, here's the area that they've said. Here's a JSON schema that represents spatial operations and place lookups. Convert the user area into this tree representation. And so using some prompting techniques and testing, and we can get to the point where we can get back this tree representation, and then it's a matter of doing that execution. And so we can go straight from this text area, this string of characters, and be able to get it to what's the area the user wants. On its own, like right away, like this by itself is super useful. We can take techniques like this. One thing I should say is that when I'm talking about this, we're not using large language models on their own. We're using them in conjunction with some code that we're writing. That prompt, or the code that generates the prompt, the code that does the spatial analysis. So here's an example where we're doing natural language discovery for catalogs. We're taking a user request, like show me Sentinel-2 level 2 items over the Senegal coastline with less than 20% cloud coverage in 2021. And we can ask the LLM to convert that into a JSON representation. There's some additional manipulation we have to do, but then at the end here, this is a stack query, right? So when we prompt the LLM, we tell it what collections are available. We tell it what properties are available on the collections. And we tell it things like, we want you to extract the temporal range. We want you to add in the natural language geocoding parts. And then what we get out is a JSON representation of this collection ID, this date time range. The LLM is smart enough to understand from property descriptions, or maybe just the property name itself, like high probability clouds percentage is what we want to use to find that. And then a user can ask a question now, and we can get just the data that they're looking for. So we've got understanding the question. What else comes next after this? So now we need to actually go about the process of answering their question. And we need to figure out the steps to do that. There's another technique with large language model called agents. And it's also called function calling, or you might have heard about tool use. There's a few different papers that all kind of revolve around different ideas, and it's kind of been brought together to this idea of intelligent agents. And basically, it's a combination of some code you write and a large language model. The code we'll call a broker. And what the broker does is it gets a request from the user, and then it knows I have these different tools that are available, these different API requests. I can do mathematical calculations and things like that. And it tells the LLM, here are some tools. Here's the user request. What should I do? How can I answer their question? Let's walk through that. So we prompt the LLM here. We tell it its job. Your job is to choose the next step to answer the user's request. Here's a list of tools, and we give it the list. They're documented. We say what parameters they take, and the user request. And so the LLM can, from this list of tools, decide, well, maybe the first step is the natural language geocoding. We need to figure out what area they want. And then maybe this response that comes back, the broker is then going to go off and do the natural language geocoding with another LLM, and it gets the answer back. And then it needs to figure out what's the next step. And so it goes back to the LLM at that point and says, okay, I needed to do this for the user. You told me to do natural language geocoding. I did that. Here's the result. What should I do next? And then the LLM can respond with, okay, now do a catalog search. look up Lyme disease. We'll find that here's the spatial area. And then we go and, execute a catalog search. We find, okay, there's a CDC data set that we can use. And so this back and forth happens until the LLM decides it gets enough information that it can actually answer the question. And so this whole process, we can be tracking provenance, the steps that are passing in order to do it, so that when we get a user the answer back, we can tell it, here's what we did to get your answer. It's not just a black box. We actually pulled data from these sources. We know what data set it came from. There's a great NOAA idea about using processes data, where they capture the steps to create data sets. And I think we can combine that approach with large language models and agents where we could figure out what process should we follow and then have it automatically track this provenance to get an answer back. So agents kind of become this overarching step where we're figuring out the steps and then it's actually the execution of them. So what comes in this last part here? What's left after that? Well, this is a lot of different things, right? This is where it's going to be really dependent on what do we need to do to answer this user's question, right? There's going to be searching catalogs, we might be counting or doing aggregations or correlations, doing classifications, et cetera, and then maybe like displaying things back to the user. So a lot of this stuff isn't AI ML. It's stuff that we do now. It's tools that you've been building, and we need to think about, or I want to say that AI ML can still help with these steps. In order to explain how it does that, I have to get to a topic that's a little bit hard to understand, and it's called vector embeddings. So vector embeddings are really the Swiss Army knife of tools that are available, and what it can be used for so many different things, like being able to search and find relevant document chunks, being able to do classification of imagery, being able to do clustering, et cetera. So I'll explain what they are. So a vector embedding is really a point in space represented by a bunch of numbers, and it's got many, many dimensions. You take a machine learning model that's already been trained, and you give it some text or an image. Some models take one or the other, some take both, and they give you back this pile of floating point numbers. By themselves, you can't really interpret anything from the number. It just represents a position in like this super dimensional hundreds or thousands of dimension space. The important thing about them is their relation to each other, but they are capturing the semantic meaning of what you're giving it. If we give it an image here of this area of land with a beach and ocean, we're going to get back something that represents the semantic contents of what's in that picture. So let's work through an example here. So if we take the word potato and we put that through a text embedding model and we get back a point, right? By itself, that's not useful. It's just, it fits somewhere in space. What really is beneficial is its relation to other things. So if we do that again for another word like carrot, we get back an embedding. Those 2 points are going to be kind of close together because of their relations in the semantic meanings of the words potato and carrot. But if we do something completely different, like defenestration, the act of throwing a person out a window, it's very different, right? It's going to be farther away. And as we start to add more words here, getting their vector embeddings and plotting them in space, you can see like windows somehow related to defenestration, but it's a thing, so it's farther away, and then house is related to window. And I'll get there to where how does this actually apply to earth science? If we try and put like more and more things in this space, you'll see like, oh, 2 dimensions gets crowded. It's really hard to capture the subtlety of human language in 2 dimensions, or everything that might be in an image in that dimension. So vector embeddings have hundreds to thousands of dimensions. And this is where people, I think, get caught up on this, because there's a lot of math involved here. And this idea of like trying to visualize where is this thing in thousands of dimensions is really hard to grasp. And what do each of these dimensions mean? You can't, like, there is no meaning for the 375th dimension. Like the model figures it out as it's being trained. It decides how it's going to use the dimensions. That part's a little mysterious, but we can kind of encapsulate that in a black box and just understand that the important part is the relations and distance. So here's an image at the top, and I generated a vector embedding for it using a model that understands the content of the image. And this model in particular is trained on images that have been tagged with OpenStreetMap tags. So it understands the content of the image. So the vector embedding for the top image is going to have forest and trees and a clearing, and there's a tiny little road at the bottom, and all that semantics is just in that single point. As I generate other vector embeddings and show here at the bottom, what's its distance from that, you can see things that are very similar. Another image with a clearing and part of a road is very similar. This next image, it's really hard to see, but it's got houses in it. So semantically, it's very different, even though, or it's similar, but it's still different because of the houses. So it's farther away. There's some construction here in this next image. It's a little farther. And then you get to a city, which is even farther away. Semantically, we're talking about semantic distance. So what can you do with this stuff? Well, first, you need to put it somewhere where you can go off and search for it and be able to do something. And so that's what vector databases are. They don't have to be special. Like Postgres can be a vector database. There's a plugin called pgvector. And basically, you can have a row that's basically like, here's a place on the earth that's, you know, got spatial and we captured it this time. And then here's a column that's the vector embedding. And we can do this with text documents. We can chunk them up in websites and things. So now that it's in a vector database, we can start to do really interesting things. So if a user wants to find things on Earth, semantically looking for what's in the image, we've generated the vector embeddings for everywhere, like on the Earth, let's say, or some area. A user can say, find me a large solar farm. And just quickly doing this vector-based search is basically just doing point comparisons to see distance. We can find all the places that are semantically relevant. So this is really cool, right? We can search inside imagery at this point. And we can build these up. We have a demo. I can show this tomorrow evening, but here's one where we're saying water treatment facilities. It found images of water treatment facilities, not by looking at any metadata from these places that are tagged, but just by the contents of the image itself and looking at the vector embeddings. We can even like start to add in the LLM things, where now we're going to get an instruction from the user. Show me algal blooms within 1 kilometer of the coast of the Cape Cod. So now we're taking natural language geocoding to get what's the precise area that they want. We're looking at just algal blooms using the vector embeddings to go and find those. And this can execute really quickly. We don't have to like spend a long time analyzing it. Vector embeddings can also be used for change detection, right? If we have data across time, a forest is still a forest over time. Even if the pixels change, the leaves fall off the tree, they grow back, trees fall and come back down, it's still a forest. So the semantic distance is very small. But as soon as something big happens, right? Somebody starts knocking down trees to do a mine, semantically, it's different now. And so with a single SQL statement, we can do change detection. We can start asking for, find me changes that are this kind of change as well. So really, vector embeddings are the Swiss Army knife that we can use. There's a really cool visualization. This is from Earth Genome. I really like this one a lot, so I'm stealing it from them. But basically, they took, here's the state of Alabama. They generated vector embeddings for a whole bunch of individual chips from those images. Then they did clustering on these images based on their vector embeddings. So a bunch of Alabama is trees, which they've colored the different clusters based on color. And then you have these other little areas, which are things that are not greenery and trees. You have roads and airports and buildings and things. And so you can do this with a model that has been self-trained. It might not even, like the models that I was showing before were trained on OpenStreetMap tags and imagery. You could take a model that doesn't even know about that. It basically is just looking for differences, and it can separate out land classification or different kinds of features on the Earth this way. Another thing we can do, I've talked about imagery and change detection and things like that, but then there's also text, right? We have knowledge out there on websites, in documents, in metadata, all of that text that's out there. So we do have the ability to generate vector embeddings from text. And so there's a technique called retrieval augmented generation. And Chad will talk a little bit about this. But basically, we want to ask a question to a large language model, and the answer might come from knowledge that's out there at your organization. And we don't want hallucinations. So a technique to help get better answers is to ground the language model with real truth. And so we can take documents and chunk them up into paragraphs, create vector embeddings, and store them in a vector database. And when a user asks a question, we can then take their question, create a vector embedding from that, and then find what are all the pieces of text that are similar to what the user is asking. And then we can take all those pieces of text that we found, pass them through the LLM, and the LLM now here's a whole bunch of text that is relevant to this question. And this has been shown in studies and papers like that this produces answers that can be more accurate. It reduces hallucination, and the LLM can do things like generate citations. So you can have a link back to the original data. So the user has trust in terms of the answer that they're getting. They can go to the original source and see that it's correct as well. So I wanted to show that there is real value here, and it's about being creative. It's not using them on their own. We have to understand the biases and the costs, but we can bring it together and do it. And happy to talk more about it. And I want to go to some other speakers now, but before I do that, I'm going to see how we're doing. Took a little bit over 15 minutes, but I think we can do a few questions between. Yes, in the back.
Jason, it's a great presentation. Absolutely. On the agentic systems, and I'm assuming you're using Bedrock quite a bit. Are you using different models based on the question that the agent comes back and asks? So you find Anthropic works best on one, and then maybe Titan works good for another. Is there anything you can say for how you're using the models to answer the question?
Sure. So the question was on what models are we using? Are we using different models for answering different kinds of questions or different purposes? I did some testing to see. I did testing on embedding models to find which ones would be more relevant, and I did testing with multiple models, like with Gemini and Bedrock and Titan Text and Claude. And really, I just found one that I liked, and that seems to work pretty well. And I really like the Claude models in Bedrock. And they just came out with a new one, Claude 3.5 Sonnet, and they're really good. And so, no, I don't tend to switch between them, because once you find one that works well, then you learn how to prompt it well and provide information to it. Yes.
I was wondering what the computational overhead for the embeddings are, especially visually, and then also how that scales with, for instance, if you wanted to include hyperspectrals, you gave, I think it's RGB embeddings, right? How would that maybe scale with something like hyperspectral?
Yeah, so the question was on, you were talking about visualization and the cost there and related to, and the embedding. So I didn't build the visualization that Earth Genome had, so I can't answer on that particular one. But in terms of searching and the computational overhead, really I think we found we could run it on an instance with no GPU to do the just compute. So it's not that bad. I don't have exact numbers to give you on running the models to generate vector embeddings. The model that we were using is a visual model, so it doesn't use the other spectrums, but we want to start using other models that do. I think Clay you can use with hyperspectral data, and there is other models that do that. And so when they're, maybe I'll stop there. Yeah. Hey, any other questions or questions online? Yes.
You have open source examples of prompts for generating a JSON from the query?
Not yet. We still have it in demo phase, but I think we like open sourcing our tools, and part of it is getting someone to help fund creating it. And then, we could do it in an open way, I think. Any questions online, Joe?
No questions.
Okay. All right. Maybe we should go to our next speaker, which is Mikey Abella.
We could comment online, repeating the question would be helpful for folks online.
Yeah, sure thing. Well, thank you, Jason. Really great presentation there. There will be a lot of similarities in my presentation. We at Earth Genome are also very excited about vector embedding. So that's a big theme that you'll see in ours as well. But hi, everyone. My name is Mikey. I am a product engineer at Earth Genome. Product engineer is kind of just a combination of software engineer and product manager. So I handle the front-end engineering for our tool Earth Index, which I'm here to talk about today. Essentially, this is a web application which we think is really useful to make satellite imagery searchable with AI and machine learning. We're essentially putting a user interface in front of those vector embeddings that Jason was talking about. So to start, Earth Genome is a really small climate tech nonprofit. Our team has a variety of different backgrounds. We've got some software engineers, some designers, some AI and machine learning experts, and some geophysical scientists as well. And our overall mission is to use user-centered design and user-centered design and data science to advance climate action. And so here is kind of our very high-level view, similar to what Jason was showing with that timeline in his presentation about what's going on in AI right now, and what has enabled something like GPT to really explode into the mainstream for downstream users who don't have any knowledge about the technology underpinning it. So the first step really is to achieve a massive scale of data, because more data means that you can train better and better ML models. In the case of GPT, it was trained essentially on the entire history of the internet. And then from there, you need to also create a really robust developer ecosystem to make those models accessible to software engineers who can translate them into really exciting technology applications. And then at the downstream end of that, to create applications to design really intuitive user interfaces to make it so that people with no knowledge about AI and machine learning can make use of these models. So this is kind of what has happened with ChatGPT, where people say that really the main innovation with GPT was putting it behind this chat interface to make it so that my grandparents can copy and paste an email that they received into this interface, ask it whether it's spam without having to know about the design of that interface, the API feeding it, the model that's behind that API, and all the data that went into training that model. But we at Earth Genome are wondering what this process might look like for the equivalent kind of model in the Earth observation space. So that first question about scale of data, we think that this is kind of already answered. We have a lot of data available to us now. This graph is showing the cumulative number of Earth observation satellites launched into orbit, which is exponentially increasing. And I talked about GPT being trained on the entire history of the internet. That is kind of true, kind of not. After filtering, the total amount of data that it was trained on was about 1 terabyte for GPT-3. And Sentinel-2, which is just one Earth observation satellite, is collecting 2 terabytes of data per day. So we have a lot of data to start training models on. But satellite imagery in and of itself is not necessarily actionable for creating insights at scale. You have to be able to translate it into something like a numerical indicator for vegetation, which is what the Normalized Difference Vegetation Index, NDVI, is doing. You can see here how it takes RGB imagery and translates it into something that indicates where there are highly concentrated vegetation areas. And there are other applications of AI using satellite imagery as well. One really exciting one that we at Earth Genome are pursuing is these kind of tracking applications using detection models. And traditionally, these are accomplished in an ad hoc way where we're training a model to detect one specific kind of feature. So here are 2 examples of things that we've built models to detect. We have a website called Global Plastic Watch, where we trained an ad hoc model to detect plastic waste sites in Indonesia and put that behind a user interface to make it so that people could explore those insights. We've also found that detecting poultry CAFOs, concentrated animal feeding operations, is something that's really well suited for these kinds of models because it has a quite distinct visual footprint. But we found that this process of creating these ad hoc models to generate these data sets was a little bit repetitive and cumbersome. And so in come foundation models, which are the thing that underpins creating the vector embeddings that Jason was talking about. So a foundation model just signifies that it's a generic model that's trained on a high quantity of data, but not for one particular purpose. So GPT might be considered a foundation model because it's just trained on the entire history of the internet to string together words in a manner that's kind of human-like, but it's not intended for one particular purpose. So you can use it to generate code, but you can also use it to write emails or to summarize large bodies of text. It's also self-supervised. So typically the process for creating those kinds of tracking models that I was talking about on the previous slide would involve a lot of hand labeling to give a solid labeled data set to train the model on. But with foundation models, this can take place in a self-supervised way. So that saves a lot of time and you can achieve a lot of really exciting insights with a lot less human labeled data. So there are a lot of these foundation models out there right now. We're making use of them at Earth Genome, and Jason beat me to the punch with this visualization, but this is essentially what's happening when you feed satellite imagery into one of these foundation models, is you kind of reproject the Earth's surface into this new high dimensional view, where you can explore, these are like 30 by 30 meter pixels, in a manner that's totally separate from what you're used to when you look at satellite imagery, and view them, like Jason mentioned, in these clusters where they are made proximate to one another, not by their geographic location, but by the similarity of these vector embeddings, which again are many dimensional, and each of those dimensions might be something like NDVI or the presence of a plastic waste site or a CAFO, which is what we're exploring in this GIF here. So where we think the opportunity with foundation models lies is really to move away from this ad hoc process of today of creating these custom models to detect plastic waste sites into a space where we can take advantage of this vast amount of satellite imagery data that we have, feed it into a foundation model, and then achieve a wide range of downstream tasks using those vector embeddings. And where we think that Earth Genome can really make impact in advancing this vision is on the last two steps of this pipeline of making impact with AI, where we think we have the scale of data that we need, we have some pretty good models, and some more are being actively developed by very smart people. But we think that some more work could be done to create an ecosystem around these models and to put an intuitive user interface in front of people so that folks with no familiarity with AI can take advantage of these foundation models and vector embeddings as well. So that's what we're trying to accomplish with our tool Earth Index. Essentially, what Earth Index is putting a user interface in front of vector embeddings, like I mentioned. So when you log into Earth Index, you're going to be presented with kind of a traditional satellite imagery geospatial application view for your specific region of interest. And then you can start to label the sort of feature that you want to detect in Earth Index using a square labeling process. And then when you click our search button, essentially what's happening behind the scenes is we're going into our vector embedding space and using the examples that you provided with your labeling, we're going to find similar examples, similar pixels, and then return those back to you in the familiar view, which is the satellite imagery perspective. And if you're curious about the technical elements that we're using, the foundation model that we use to generate our embeddings is SSL4EO with the Dino visual transformer objective, and we're using primarily Sentinel-2 imagery to train that. And so here's where we're currently at with our tool Earth Index. We wanted to turn it into something that was very usable, that didn't require any pre-existing knowledge about foundation models, and that was also kind of delightful to use as well. It's kind of a buzzword in UI. And we also really wanted to focus on the speed at which you could achieve insights. So we wanted you to get to kind of like an 80% accurate data set for your specific feature of interest in like 10% of the time that it would take before. And initially we developed this just for internal applications, but we decided that it was a useful enough tool that we should seek philanthropic funding to turn it into something that folks outside of Earth Genome could use as well. And as we engaged in that process, we decided to focus in particular on putting it in the hands of Indigenous communities on the ground. And this was because Indigenous communities care for about 80% of global biodiversity while making up only 5% of the population, and have not historically been afforded the access to their land or the resources in order to steward that land. So we think that Earth Index could be a really great tool to connect the gap that exists right now between a lot of funding moving into the space of advancing Indigenous land stewardship, but kind of lacking the actual on-the-ground deployment, because a lot of the time these funding sources have pretty strict requirements on project tracking and monitoring. So Earth Index is a great application for achieving that. We also recognize that there's a reason that the current approach uses these ad hoc models, because detecting one specific feature might look really different in one region of the world than another. And so local context really matters. And these Indigenous communities or other local populations are going to be the best poised to be able to recognize what the local context might look like for environmental degradation happening on their land, and also the best poised to take action to put a stop to it. But we also recognize that we need to advance this mission beyond just the capabilities of Earth Genome as an org. And so we're looking for partnerships with data journalists and data scientists at like-minded organizations as well. And I'll get into one of our specific applications for Earth Index where we found some success. So we looked into the Yanomami Indigenous Territory, which spans several countries in South America. And in particular, we were focused on investigating their land in Brazil, where there's a lot of illegal gold mining taking place. You probably read some of these headlines. And in the previous Brazilian presidential administration, this was kind of allowed to run rampant. And so it's very negative for the Yanomami people, because oftentimes this illegal gold mining uses mercury to separate the gold from mud, and this poisons the water supply, leads to high infant mortality rates, disease, and also sometimes conflict between the Yanomami people and these miners themselves. So we wanted to see if Earth Index could be useful in trying to find these gold mining sites, especially with the arrival of President Lula, who was actually deploying forces on the ground to shut them down. But this is a pretty difficult problem because miners are moving around very frequently. The Amazon has notoriously high cloud coverage, and there are other sources of deforestation which might introduce some noise into applying a model. But we found that Earth Index was pretty successful. Using it, we were able to find that the previously understood amount of land that was impacted by this was a huge underestimate. It was actually 3 times larger than was understood using the findings from Earth Index. And then we were able to really amplify these results through our partnerships with different journalistic outlets. And we're looking for similar kinds of applications of Earth Index where there's a sympathetic government in place that wants to allow these Indigenous people to advance the vision for their land that they foresee. Another example that we found a potential partnership is in the Solomon Islands, where it's illegal now to conduct deforestation above 400 meters. And so we're working on getting Earth Index into the hands of folks on the ground there who can monitor their own land and bring these illegal instances to the attention of the government, who can put a stop to it. Really, the main thing that we've learned from using Earth Index for our own internal research is that it can really accelerate the time to impact. So Global Plastic Watch was one of those ad hoc products that we created before, which took many hundreds of days. We took the results of the Yanomami gold mining research project and turned this into a website called Amazon Mining Watch, which took significantly less time to put together because we employed Earth Index. And we're now also using Earth Index to find poultry CAFOs in collaboration with Climate Trace, who's going to use the data set to generate some estimates for emissions from poultry CAFOs going forward. And that just took a handful of days to put together. Where the tool is at right now is we're in an alpha release that just came out in May. We are invite only right now, so it's not open access quite yet, but we're looking for new partners through our AI accelerator for Indigenous communities, as well as through a partnership with the World Bank. And we're targeting a September release for a beta version of the site. As preparation for that, we're looking to further develop the ecosystem around vector embeddings by developing some new data standards and open source libraries, as well as making some of our data publicly available, like the Sentinel-2 imagery that we used to train and create Earth Index. We're also working actively on developing more robust feature sets for the tool, like comparisons between time periods, subannual monitoring, and global embeddings. So that sums up my talk. Thanks for listening. And if you want to sign up for the waitlist or learn more about Earth Index, you can scan this QR code. Thank you. I don't know where we're at on time, but should I take some more questions or?
Sure.
Okay. any questions?
You mentioned that there's literally exponential increase in the number of satellite mission, the amount of data. You mentioned, you had a really nice graph showing, especially how the number of private sector and NGO space missions is increasing. So the amount of data, non-public sector data is increasing a lot, very fast. And it's probably just gonna go up even more. So there's a lot of change, there's a lot of churn. How can you talk about how your project will keep up with that amount of data, as well as just the normal change in the earth, as well as the changes that you're trying to monitor?
Yeah, it's a good question, and one that we're a little bit early stages in addressing. Right now, we're just using Sentinel-2 imagery for the most part, and sometimes Sentinel-1. So I don't know that we have the answer to that yet. There are probably going to be even more exciting insights and metrics that we can develop using different types of these satellites that will be launched into orbit going forward. But right now we're trying to just kind of figure out how to access that imagery and make it impactful through the tool right now. Yeah.
Yeah, thanks. This is really interesting and exciting. Though I sort of want to build on this question. Like, there's a huge exponential growth in the sort of total volume of satellite imagery and things like that. But to me, like the most valuable data sets are in the long tail of that distribution. It is the small boutique data sets, right? So like, I think I had a professor in grad school that said like remote sensing is the art of sort of detecting the obvious. Right. And so like in many cases, it's the field measurements, it's the tower measurements, it's the airborne in situ measurements that are the most valuable and giving you the most precise information. And so I wonder with like this effort and other efforts, what is your strategy for tackling that long tail of small but incredibly detailed data that's on exactly the things that you want, rather than the satellite imagery that's giving you sort of a broad brush and then you're doing a lot of inference on those satellite measurements?
Yeah, that's a good question. I think the way we're thinking about this is probably partnerships with folks that are experts at using those kinds of data sets and figuring out a way to combine the labels and the data sets that you generate with a tool like Earth Index with those other indicators as well. So for example, we are very excited about on the ground confirmation of like an illegal gold mining site, for example. So would there be some kind of way to combine Earth Index into a suite of other tools to allow for kind of like hand labeling and annotation of a map layer that would include Earth Index labels as well as some of those other things that you were talking about. So right now, I would say that would be kind of a complementary tool to exist alongside Earth Index. Any other questions? Yeah, down here.
Just about the indigenous imagery. Just some mental models, right? Is that like if farming is, for example, rice farming in South Louisiana may look one way in imagery, in other communities, more rural communities, would it look different? Am I thinking about like why this is important to be able to identify the images based on the location?
It's really just that in different regions, the same activity might have a slightly different visual footprint. So it can be kind of hard to generate a global data set for rice cultivation, but using a tool like Earth Index, using vector embeddings, because it relies on a foundation model process where you're using these kind of visual indicators. So where we've found more success is like regional level data sets, but it still is really useful at, for example, finding CAFOs across the entirety of the southeastern US. And there was one more down here.
Thank you. You mentioned that I think it was the Earth Index could get to like quickly answered like 80% of what you needed to figure out. How hard is the next 20% and how important do you see that being?
Yeah, that's another really good question. So it's a trade-off that we made in this approach right now, is that, yeah, you can get to that 80% accuracy pretty quickly. Getting that last 20% might end up taking 90% of your time. So we think this is really good for kind of establishing a baseline right now, and a lot more work has to be done to create the complementary tools that might go into advancing that last 20% to get to the finish line. So if you need like a really hyper accurate data set, it'll take some more work than just a minute, but we think that 80% accuracy in a minute is pretty exciting as well.
Let's go to the next.
Yeah.
Speaker.
All right, hi, everyone. Thanks for having me today. My name is Chad Melton. I'm at Oak Ridge National Laboratory, and I don't think I really know many people here. So about me, I am a research scientist at Oak Ridge National Lab. I have a background, a large portion was in geology and planetary science with a focus on remote sensing. My PhD was in data science and engineering. This is what got me into the study of natural language processing in the context of public health surveillance. So at Oak Ridge, I work a lot with environmental determinants of health and toxic release. And also a big portion of my time is related to NLP and transformers. So if you see me, you want to talk about any of those throughout this conference, please say hey. Also with a background in geology and planetary, if anybody just wants to talk about geology, reach out because I miss it sometimes. But okay, so today I'm going to talk to you guys about large language models in the applications in the domain of environmental transportation. So we've gone through some of this, but just to make sure we're all on the same page again, large language models are these advanced AI systems that are based off of transformers or deep neural networks, and this gives them the ability to understand language. These are, as we've said before, they're extensively trained on large corpora of data, and this allows these models to learn syntactic constructs and as well as context and conversation and imagery, which is great. So a great aspect about these is they can emulate human conversation and tackle a lot of different problems. The best part about these, and for language specifically, is they can be customized for specific tasks. And this can be either in fine tuning with your own labeled data and training the last layer of a network, or using a tool such as retrieval augmented generation, which I'll talk about a little bit. So a big problem with them, as we've talked about somewhat, is hallucinations here. And I've got some great examples I'll show you later. But I think this is what's really slowing widespread adoption whenever you have a lot of safety things on the line, like public health or safety. And like what I'm talking to you about today, we can't afford to have any mistakes because it can mean a lot of lives and at the very least, a lot of money and fines. So for some historical context, this all goes back to a development called BERT. BERT was developed at Google in 2018 or published in 2018 by Devlin. And this really propelled NLP into a new era. At first, it was based off of pretty much like lexical dictionaries where you would have valences or a number attached to a word for things like sentiment analysis. But looking back in history books in 20 years, we'll look at this as the change from the Stone Age to the Bronze Age, and we're still early in it. Typically these are designed into two different types of tasks. You can have classifiers or generators within BERT. And the way that BERT specifically was trained, we've mentioned embeddings, and so this just takes words and essentially stacks multiple encoders for the classifiers. The generators will have a decoder encoder architecture, which makes things like translation possible. And so BERT specifically, what gives it the ability to understand context is the way it was trained. And they're not all trained this way. There's different variations, and this is what's improved a lot of the performance. BERT itself was trained with mask language modeling and then next sentence prediction to where in the training of the algorithm, it would randomly mask words within a sentence and then predict possible words that could be in there, and they would offer some probability back. And so BERT, after its development, it could quickly expanded into these models, all these different variations of BERTs with different parameters. And this exploded then into various Sesame Street themed models, some classifiers and some GPTs. We're moving out of Sesame Street, and this is a little bit older, so this would actually be quite expansive now. And so the application of these is truly vast. Some of the popular applications that I've played with are a sentiment classification. I tracked COVID vaccine perception throughout the pandemic for my dissertation.
and public health surveillance. I've also worked with a group at RNL where we work on classifying tumors based on pathology reports provided by the SEER data set. And I've been interested in route planning, and I want to get more involved in image description too, because it's the work that you guys presented today is really fascinating. So I'll be talking about the GPTs mostly. So these are popular that you guys are probably using without knowing it maybe. You've got Bard and Gemini, you've got ChatGPT, Meta's variations of Llama, and then Microsoft's Bing AI, and then several others. And these are changing all the time. This was taken from a leaderboard on huggingface.co. If you're not familiar with this website, go to it. A lot of these models are available there to download. And if you have the infrastructure or a computer that can handle it, these are freely available for you to fine tune or augment them. But this has, you can see how the parameters have expanded quite a bit, and some of these should be quite interesting to experiment with. So I mentioned the difference between fine tuning and retrieval augmented generation, where this is where you have a model and you need to access data that are more recent, perhaps, or that this was not including with the original training data. So you can create a popular method is a vector database, which was what we did. And this is a pretty busy diagram of a system that we built to test some things that we're experimenting with at the lab here, where we have some type of model here, some GPT, a generator interface with a web UI where a user can go in and query. The model can then reach up to the, can you guys see my mouse? You can't. Okay, I'm just making circles. Okay, so we have some model here, go to a user, and then that can be connected to the vector store, where then this all works out nicely for a user prompt. I was thinking you guys were seeing my mouse the whole time. I'm so sorry. So our use case was in this domain of transporting hazardous materials. So if you didn't know this already, you can't just get some radioactive material and drive it from, say, here to Los Alamos. You have to have permits, you have to have specified routes, and there's a lot that goes into it. And this creates a huge amount of documentation, federal and state regulation that route planners and the people responsible for obtaining these permits must know. So we thought this would be an interesting application to test this for some people that we work with at the lab who are responsible for getting rid of some hazards, not just radioactive material, but other hazardous materials from A to B. And the flow chart here of our work, we worked with a domain expert to gather the documents that were needed that specify these regulations. And then we also employed him to develop about 100 queries that we could then test. So while he was doing that, we were busy developing this infrastructure I showed you in the earlier slide, and where we tested so far just ChatGPT 4, the Vertex AI, and then Llama plus RAG, and now Llama 3. We tested that as well, and we planned to test more. So once it was built, then we could run everything and then get our results. And then we conducted a qualitative analysis and then a cosine similarity analysis, where the qualitative analysis involved just 3 of us due to time, evaluated these manually, and we rated them on a scale of 1 to 5, 1 being the absolute worst, so involving a hallucination, and 5 being best. And so we developed this criteria here where we all tried to rate these, and then the results then were averaged and then compared. This is just an example of the three different systems. The query was, what is a reportable incident? So if there was some type of spill or security incident, and these are the different responses. We see ChatGPT's is fairly high level, and you get a good information between Vertex AI and Llama, which could be the rating of this could be subjective depending on who is asking the question. So our overall results with this the Llama 2 plus the retrieval augmented generator that we built scored an average of 4.03. It was pretty thorough most of the time. The alarming parts of it were you would have one paragraph have one statement, and then the second paragraph contradict that first statement in the same response. So this was an area of concern. Vertex AI was second best, but we got some false information with them, which knocked down their score. And then GPT was 4 was the lowest at a lot of hallucinations popped up in there, and then some of the answers were somewhat remedial. The cosine similarity essentially measures the similarity in vectors. And so to quote Richard Feynman, if you like math, here is the mathematics behind this. And where a score of 1 would give you an identical vector, and 0 would be completely orthogonal or not similar at all. And this is what the distribution of these look like when we compare them between models, where the llamas would be expected are very similar. The Vertex and Llama 2 are next, and you can see how they played out coming through the rest of these. But this was interesting to look at and compare with our qualitative analysis. So we thought that there were some really some great aspects that we discovered, and I can't go through the 100 queries, but there were some really wonderful answers provided. This was a great failure when we first started experimenting with the idea of connecting one of these to something like Waze or some type of app that had the ability to give traffic information. But it did great with recognizing this image of downtown Knoxville, but the failures were pretty great, where it detected biohazard symbols, radiation symbols. It detected biohazard symbols and radiation symbols, which there was no radioactive or biohazard catastrophe in Knoxville that day. And the second really great one. So I gave the bullet points for this research here, and this is the flow chart that ChatGPT generated for me. And hopefully this didn't come across the same way to you, but yeah, so some work needs to be done. And that work I really think lies in evaluation, and try just to remind people who use these models, you really get out what you put in to a model. And that's working with naive users don't truly understand that yet. Some sponsors that we've worked with seem to miss that. We'll build them a demo and then they'll ask questions that just have nothing to do with certain things. So trying to reiterate that to people. But these are things that we want to work with. I want to keep testing models and then really hone in on route planning, just because route specification is a big deal. You can't take certain roads. Like if you drive through Knoxville with certain shipments, you have to take 640 near my house rather than drive through downtown. And then also map readability is an area of interest to us. But yeah, I would just say the big take home from this is please develop evaluation methods, and that's something that we're trying to build a lot in these, especially if you have if you have more than probabilities on the line. And I think that's all I've got. I'll be happy to take any questions.
Thanks, Chad. When you were evaluating the different models, those were all using RAG?
Yes. Yeah.
Okay, did you optimize the prompts individually for each model, or was it using the same prompt?
So it was the same prompt for each one. That we had the domain expert created this for things that questions that he thought was relevant. So we didn't play with articulation and some of them better. We have experimented with that on our own, but not in this formal process. Of course, when we play with them, that's a big deal. I think being able, like I've noticed too with coding as well, if you can be really articulate with the coding tasks that you want, then it can give you really great code. But I think that they typically will respond well to that. But,
thank you.
Have you played with temperature at all to fight hallucinations?
I think somewhat. Another colleague played with that somewhat when he was building, but not extensively yet, just due to the time constraints on all of our team.
Yeah, I was doing a little work trying to see if I could get a more reliable answer or a more consistent answer. Ask the same question, get the same answer twice, and I was playing with temperature. I was just wondering if you had that.
Yeah, temperature is a great thing you can experiment with. Yeah, thanks for bringing that up.
You might want to tell people what temperature is.
So temperature will help to measure either I guess the correct amount of, or the amount of text that you want. Like you can, like some of the llama text that we had, and if I'm explaining this, please someone jump in if they can say it better than me. We'll give you, large paragraphs or, hey, thanks for asking this question, versus give you an itemized list. So that's,
Like how creative the model is.
yeah. Yeah, that's great. And then, yeah, so he said how creative the model can be is a great way to explain it. We've also found a good way to try to track hallucinations is getting some of the models to provide a citation from the document where we've uploaded to within the RAG, which is helpful. But yeah, thanks for mentioning that.
I think we should probably.
Okay, sweet. Thank you.
Yeah, right.
Oh, in Chrome, gotcha. Okay, I gotcha. Okay, great. Hi, my name is Tyler Christensen. I work for NOAA NESDIS, which is the Satellite and Information Service for NOAA. I do not have a PhD in AI machine learning. So what I am, I'm an open data expert. And I've been for a couple of years looking into this idea of one of the unique assets that federal government can bring to the table in this world of AI and machine learning is our data. And it's a unique asset that really only federal agencies can provide. And how can we prepare that data to make it easier to use in this world of AI and machine learning? So this is one effort that I've been involved with, but it's the intersection of AI and open government data. What I'm going to talk about right now is an extension of what we heard in the opening plenary this morning. We're looking at this from a Commerce Department perspective. So NOAA is part of the Commerce Department, along with NIST and the Census Bureau, and so there's a lot of data intensive agencies in the Commerce Department. So we're trying to think more broadly, just outside of NOAA, but across the whole Commerce Department. How can we make our data more AI ready? So this is a priority area that we're thinking about, especially as part of one of the new data strategy that we're putting together. And it's part of this idea of machine actionable data. So not just individual NetCDF files that you can read, but it's taking that machine, that sort of machine readable data and expanding it into something that's machine actionable. So machine readable, this was sort of how we were thinking about data. You want to put it out there in a machine readable format that can be automatically ingested and processed by a computer, as opposed to like a PDF file that's got like graphs in it. You want to actually provide access to the actual data in a machine readable format. But we're moving into this world of machine understandable. So we're talking more about structured data, and especially about the semantic context that goes along with that data. So standardized schemas with enriched metadata, and then semantics expressed in something like a knowledge graph. So you're making it so that that a machine can not only read into the data, but actually understand the content and be able to use it. Okay, so when in this Commerce Department effort that's talking about AI ready data, they're talking about specifically how do we prepare open government data for large language models to use. So separately, we're talking about other, especially internal to NOAA, how can we prepare our data so that our own scientists who are doing our own AI-based modeling can use it for all kinds of applications. But for this Commerce Department thing, we're specifically talking about open government data, so data that we're providing to the public, and specifically for use in large language models. So we've talked a lot about large language models in this whole session. I've personally learned a lot, but basically from my sort of open data perspective, there's some limitations to these, especially public large language models. They're trained on a snapshot of the internet. They don't have access to current information. But most importantly, they're trained for language fluency and flexibility, but not necessarily to be able to provide actual, factual accuracy. That's not their strength. So we need to do some extra work to help them be able to give factual answers. Okay, so the current idea that we're working on for being able to prepare our data for use in large language models is standard APIs. So APIs that conform to certain open standards, so not like a custom developed API, but a standard API that goes along with a knowledge graph. So the idea is then that the large language model can draw facts from these data sources and understand them to be able to provide answers. So it's mostly not about training the models. It's about you have a pre-trained model, but it's providing live data to the API, to providing data to the large language model to be able to answer questions. And the knowledge graph is there to give structured metadata to understand the parameters. So basically the strength of these large language models is language. And so you need to, especially structured text. So something like a knowledge graph gives the large language model more information about the data and about the parameters that are available via that API in language, so that the large language model can actually understand. Instead of like using a code SST, you use sea surface temperature, so that and you define what sea surface temperature means, but you're especially providing it in actual language, so that it can use the strengths of this large language model to be able to understand and interpret the data and use it to provide answers. So the idea, this is a figure from the Census Bureau, which is one of the Commerce Department agencies that's especially super interested. They're the ones who are leading this working group. And they really want to be able to provide all of the census information as a authoritative source to be able to answer questions like, what percentage of my neighbors have PhDs? So this is one of the things that you can draw from census data. And they want it so that if somebody asks this question using a large language model, it'll know, oh, I need to go to the Census Bureau, and this is how I can access the latest information for this location. So the idea is somebody asks a question, it goes to this large language model to be able to understand the context of the question, the location, what does it need to have a PhD? So all of those like strengths that the large language model brings. And then it goes, the language model actually builds an API query. So it actually puts together the text to query that API. Then it goes out and gets the data. It comes back as a structured response that then gets retranslated back through the large language model to be able to give a plain language answer to the question. Okay, so as we were talking about there, we've come together across these Department of Commerce federal agencies in a working group. And so the idea is, how can we work together across the commerce agencies and hopefully across broader government to come to a common understanding of how we structure our data so that it can be used by these large language models. And the more consistent we are across commerce agencies, and the more we learn from each other's expertise, the easier it's going to be for people who are coming in from the outside to understand data from the Census Bureau and NOAA in combination. So we're trying to be consistent in how we do this. So we stood up this working group under the Commerce Data Governance Board. Is chaired by the Census Bureau, as I said. They're sort of leading this effort, but it's got representatives from across all of all of these commerce agencies, including NOAA. And the idea is by the end of this calendar year, we'll develop guidelines for agencies to publish data so that it can be used by generative AI. So one of the ways that we're trying to understand the landscape better is by this request for information. So we were seeking input from experts, especially in private industry, academia, NGOs, et cetera, who want to be able to use federal data and have advice for us. So as you heard in the plenary this morning, it was organized around 5 different, so there were questions within each of these areas. So we wanted to hear about data dissemination standards, accessibility and retrieval, partnerships and engagement, how do we ensure data integrity and quality, and then obviously data ethics is foundational to all of this. So the RFI just closed last week, so we're busily trying to understand and absorb all of the responses. But here's just a few, just very early days information about the responses that we received. So we got 34 responses, which was, it was funny because at the beginning of the day on July 17th, there were about 10. And of course, by, everybody submits their things at the last minute. So we were very happy to get these 34, even if they came in at the very last minute. Mostly from private industry and mostly from tech companies, who are sort of the leaders in this area. So we were not surprised at that. We got four academics providing us responses, 8 from nonprofits or consortia, and 1 from the general public. So just a super early look at the emerging themes. Some of these responses were very, very thoughtful and gave really detailed and nuanced answers to all of those questions. And so we've got a lot of work to do to analyze those and come up with some commonalities. But some emerging themes, there was a lot of individual standards that were mentioned. Open API as a standard for how you build an API. So that was mentioned in a bunch of the different responses using those open API standards. Data licensing is incredibly important. This is something that we're just beginning to tackle at NOAA, but you need to make it very clear when you publish your data how people can use that data. And it needs to be like a legal definition of how that data can be used. Because a lot of private companies, if it isn't a very clear open license on the data, then they are reluctant to use it because it's not clear if it can be used for commercial purposes or not. So anyway, standard open licenses are a key part of that. Automated quality checks to be able to ensure that the data are of very high quality and communicating information on the data quality. Providing data previews so that people can see the data, just take a look at the data before they decide whether it's something they can use or not. So we asked about data ethics, and most of the responses seem to be use existing frameworks for data ethics, that there's a lot of work that's been done in that area already, and we should just be using existing data ethics frameworks. There's been a lot of interest in jointly working between federal agencies and the private sector and academia. We've had a couple of workshops that were sponsored by the working group and brought in some folks who were data users in either in nonprofits or in private industry, and just having a conversation for a day about how the data is used and us understanding better the data user context and them understanding better our data provider context have been super helpful. And so we're hoping to kind of come up with some way that we can continue this like bilateral communication between the data providers and the folks in academia and industry who are trying, and NGOs who are trying to use the data. And it warmed my heart that almost every response, on every page of every response, it comes down to metadata, right? You need to document as much as you possibly can in as complex and nuanced language as you can about your data. And that's how these language models that are, that's their strength, is language. The more information you can provide in plain English about the data, the better the large language models can understand and be able to like reliably interpret it and provide responses back. So it warms my heart because metadata is not the easiest sell. You know, if you if you say we as a federal agency want to modernize our metadata, right? Nobody's going to fund that. But if we say this is a key thing, like we're not lying, this is a key component to making our data AI ready, right? And it's a legitimate. It's a legitimate claim. Like we have the information here that literally every page of every response was talking about metadata in various ways. We can just make it a key component of our AI ready transformation strategy, but really it comes down to metadata in a lot of cases. So that made me very happy. Okay, so just to bring it back, why are we excited? So we're bringing it back to kind of the themes of this workshop. Large language models allow access to information just by asking questions in plain language. You don't have to be an expert. You can just say, what's the average income for my neighborhood? Where should I go fishing for a certain species of fish today? And people are already using them to access information. You know, it's a brand new tool that really makes it easy to access information about so many different topic areas. But we need to make sure that these new knowledge brokers, you know, new places that people can go to get information, can access real facts from authoritative sources. And in a lot of cases, the authoritative source for those kinds of information are federal agencies. So if we make this public data easily accessible and interpretable, we really want to make this data easily accessible and interpretable so that all Americans can benefit from insights found within our vast collections of information, and especially within the Commerce Department for economic, demographic, and environmental data. So we're kind of trying to unleash the potential of all that data in a responsible and ethical way, but making it so that you don't have to be an expert user, but you can actually just, in plain English, ask a question and be able to get real information from authoritative sources. So thank you. So I guess we have a few more minutes. We have 7 minutes for questions. And those questions can be for any of the speakers, since we're at the end of the session here.
Thanks, Tyler. That was a great presentation. So my question was about provenance for data. So like, I think we as sort of publicly funded federal agencies, I'm with NASA, you would know, rely a lot on like people knowing that we measure things really well, and then like those measurements need to continue getting funded. Like I think even now we already face this problem of like, I think the NOAA version of this is like, why do you need the Weather Service when you have the Weather Channel or AccuWeather, right? And it's like, without a lot of people don't understand actually, oh no, these are foundationally dependent on what the Weather Service does, right? At NASA, the version of this is like, why do we need NASA observations when we have Esri's Living Atlas, right? Or Google Earth Engine, right? We again don't trace the provenance. And like that's sort of relatively basic things. I think once you start getting into like vector embeddings with lots of data sets, like all of this sort of is like super obscure and you're just interacting with a chatbot that like who knows how many data sets it's accessing, right? That becomes like 10 times harder. And so how is NOAA thinking about this in the Department of Commerce more generally? Like how do we preserve the provenance and say like, oh, and by the way, this query that you asked was influenced, not been possible without such and such data sets, that they're sort of a key foundational part of being able to answer those questions.
Yeah, that's like how you do that is definitely outside of my area of expertise. I'll just add that the kind of the other side of that coin is also something that that makes our scientists really nervous, which is how if something is attributed to us, like how do you make sure that that is like the worst case scenario for our scientific reputation would be according to NOAA and something totally false, right? So that is something that that we're going to have to basically prove that in you know, by doing experiments to prove that it is possible to preserve our scientific integrity and, you know, ensure that the questions are correct, that the answers are correct, especially when they are actually attributed to us. But also even things like, that we, you know, with satellite data, you can look for signatures that indicate that a wildfire might be present, right? But it's not, we're not saying there's a wildfire there. We're saying, we're giving a nuanced answer, which is, you know, according to satellite data, thermal signatures from satellite data, you know, there's indication, but you should talk to CAL FIRE, you know, like for as the, you know, and so giving that sort of nuance around an answer that comes from our data is also something that makes our scientists really nervous. Because if you come to our website, there's disclaimers on it that say, you know, just thermal signature, you know, talk to your local fire department, you know, to get the real. So anyway, there's a lot. In my mind, we have a lot more questions than answers on those kinds of issues. Yeah.
I wanted to,
Please add to it.
yeah, I was gonna add, yeah, I was inspired by something else that NOAA has done with, and I mentioned this in my talk related to provenance, where they have this concept of process as data, and they would represent the steps that you need to go through to produce a data set as a set of, you know, points, right? And you would represent that as data. I think that we can take that same approach with LLMs answering questions, right? If they're, you know, in the diagrams that Tyler showed, right, the LLM's going off to find data and it's doing this other thing. The LLM can answer back, say, I did this, you know, I went to these particular things. And that can all be provided along with the LLM answer. At the bottom, you can expand it. You can link back to the original data set and to that data set's provenance and everything.
Yeah, I have a question, and this is for any of the presenters, and this is something I'm trying to get insight into this week here at ESUP, is how do you all think keywords, vocabularies, ontologies, you know, play a role, either help or hinder like that work, and you know, like with use in AI and machine learning?
I'll go ahead and try to answer that one.
I know that's a little.
Yeah, I am not as knowledgeable on the idea of vocabularies and ontologies, but I was thinking about it recently. I was having a conversation this morning about it. And on in-Earth data search, if you're familiar with the NASA tool, right on the left-hand side, someone I was talking to was saying, like, people like to be able to go down through a nested list and things are categorized. People like things to be categorized as like they know where to find things, right? It has a location. So I think it does have a value, but then again, with vector embeddings, right, like I talked about, human language is so complex and you're trying to represent it kind of with a one-dimensional structure, all the meaning of what this data relates to, like maybe we need both.
So I am an expert in ontologies, and I will say that they are foundational for this. But that has nothing to do with what I have more of a comment than a question. I was very intrigued by the example question that you had, like, show me where are all the cases of Lyme disease within Boulder, Colorado? Because there you're asking for people's personal health information, which is very interesting. And that's the space that I work in. And as I'm watching this, I'm very interested in being able to use this sort of information to gain insights into things like Parkinson's disease, where we know that there is a huge environmental component, but we don't know what it is. And so I would like to say that I am chairing a session on Thursday about bringing together geo and clinical data. So if anyone has interest in this, I hope some of the speakers will come to that, and that's Thursday morning.
Thanks.
I just want to say that when you label your data sets to make them AI ready, it's really helpful if you are using vocabulary, yeah, and ontologies that create semantic consistency.
Yeah, and I have a quick comment as well. I'm Ken Casey from NOAA's National Centers for Environmental Information. And Jason, thanks for calling us out a couple of times there on what we're doing with our new cloud archive system. I just wanted to kind of give it a name and give you some folks in the room today you can talk to. So it's the Open Information Stewardship Service that we're building with OAS that is leveraging knowledge graphs and a semantically enabled framework to do all the kinds of things you're talking about here. If you want to learn more about it, I don't think we have a session on it at the CSIP, but you can talk to me, Nancy Ritchie, Kenny Chadson back in the room. Who else? We got Charlie Burris here working on it, and Ryan Burkheim is really our chief architect. He's somewhere around today, but Steve in the room. So it's called OISS.
Make one more comment related to ontology since we're on that real quick. So talking to research scientists, they hate standards and ontologies because they don't like being told what to do. And so one of the things that we're discussing, so I'm at Lawrence Berkeley National Lab, my name's Alicia, and we do quite a bit of work with people that generate ontologies, especially in biological sciences. And so I'd love to actually think through how to apply LLMs to pull out words that people typically use and then say, how about this word? Instead of us telling them what words to use, have them tell us what words to use.
Yeah, one bit of work an ontology can do in that space as well is to map synonyms so that in your search application, I can put in, radiative flux and the application knows I need irradiance, right? I think that that's a really easy and obvious tool that we should be relying.
So we also, so we've been talking about that a lot in this working group, and we've been looking at the concept, because try telling a federal agency what terms to use for things, right? And like you're not gonna anyway, but things like crosswalks can be super helpful where it, like you say, synonyms, but also related terms, and how is this thing related to that? And there's a construct called NIEM, the National Information Exchange Model, which is basically how to crosswalk federal data sets from different agencies. And it doesn't currently cover things like earth science, but we have talked about where there's a construct like NIEM, where it's about crosswalking different terminology from different agencies rather than trying to tell people what to do. I think that is something that can be much more helpful. Yeah, much more possible, Anyway, I think we're 3 minutes over. If we I think maybe we should release everybody to go get a sandwich. So thank you so much for coming. Thank you for the great discussion.